In this video, I'll talk about what's meant by without loss of generality. Now, this is something that you'll see in some proofs and you can use in proving things. And it's a nice little trick to get around doing some work. In a sense, it's a little trick you can use to be lazy. And that's okay in mathematics. It's okay to be lazy so long as you know that nothing is lost by being lazy. So, right, you don't want to be lazy by not stating your assumptions or by, assuming something is true that isn't true to get around work, because then it wouldn't really be proving the statement. But there's some cases where it's okay to be lazy. Before I get into this result and this idea, I want to share with you a little story, and that is when, back in the 60s, during the space race, the U.S. And the USSR were both racing to get into space. Now, both of these two superpowers had a problem with once they got astronauts into space. They were trying to figure out, how are astronauts going to be able to write things down in space? Because in microgravity, fountain pens, wouldn't work the same way. There wouldn't be gravity to pull the ink down into the tip, and they wouldn't be able to write. And the astronauts had to be able to write to record things and stuff like this. So they both had these two tasks, and the U.S. put millions of dollars into developing a pen that would work in space, the ballpoint pen. And now we use ballpoint pens. Just one thing to come from getting to space. That's a side note. Anyway, so the U.S. developed a new pen and spent millions of dollars to build this thing. The USSR, they used a pencil. So here was one case where, one of the superpowers they didn't want to put in all the effort to develop a new kind of pen, so they just used an old technology. They used the pencil. All right, this story isn't really true, because using a pencil in space is bad for a number of reasons. In particular, when you write things down with pencil in microgravity, right, the graphite breaks off a bit, and then you have floating graphite particles floating around that could get into various systems and mess things up. And so it's not quite a true story. I don't believe the Russians actually used a pencil. I think they developed their own pen. You can look that up if you want. Maybe I'm wrong about that. But apparently this story is false. Anyways, it brings up a good point that, if you can be lazy and get away with it, then it works. And there's another common saying with mathematicians. I'll share one more thing with you before we get into this result. Sorry, I know I'm rambling. And that is, a common expression is, the best mathematician is a lazy one. The idea here is that if a mathematician can get around doing work, can avoid doing work, can avoid writing out a whole terrible proof by doing it in some easier way that requires less work, then they'll do that. They'll be lazy. And so if you can spend a little bit more brain energy on coming up with a better way to do it, well, that's a nicer way to prove a result or to execute a task, is to think about how you can do it in the easiest possible way. So this is really just about efficiency, that do things as efficiently as possible. Okay, so let's get into this. Without loss of generality is one way of going about this. So here we want to prove this result. Let m and n be integers. Then m times n is odd if and only if m and n are both odd. So here we have an if and only if. So we know we have two directions to prove. We have the forward direction. M and n is odd implies m and n are both odd. And we have the backward direction. And that would be that m and n are both odd. imply m times n is odd. I'll make clear both odd. Now, in this backwards direction, m and n being odd implies m times n is odd. That's going to be easy enough to do directly because we have leverage. We can write m as 2k plus 1 and n as 2l plus 1, and then we can multiply them together and see that it's odd. The forward direction, though, assuming m times n is odd, well, we don't really have a leg to stand on. So this one we're going to go by contrapositive. So I'll write this one out. So the contrapositive of this would be the opposite of m is odd and n is odd. So notice that would be m is even, or by De Morgan's law, or n is even, right? I need to negate this whole conclusion, m is odd and n is odd. So that would be m is even or n is even. Implies m times n is even. So that's one important thing to note is don't forget about De Morgan's law when I negate this conclusion here, m is odd and n is odd. That should be m is even or n is even. And we'd be showing that m times n is even. So notice we would have two cases here. M is even or n is even. This is where we're going to use without loss of generality. So let's prove this. I'm going to prove the backwards direction first. So I'm going to assume, let me put a little backwards direction here. Assume m and n are odd. Then, okay, we have m equal to 2k plus 1 for some integer k, and n is equal to 2l plus 1 for some integer l. And so now I can multiply them together. So m times n equals 2k plus 1 times 2l plus 1. Don't forget to do FOIL, or however you like to multiply binomials together. This is 4kl, 2k times 2l, plus outer 2k, inner 2l, last 1 times 1, 1. And this is clearly odd because I can factor out a 2. So this is k times l plus k plus l plus 1. Hence, m times n is odd. All right, backward direction's done. Forward direction we're doing by contrapositive. So we'll assume m is even or n is even. So that gives us two cases to consider. Case 1, m is even. So, okay, if m is even, then m equals 2k for some integer k. And I want to show, remember here, I want to show that m times n is even. I don't even need to write n as anything here. I don't need to split it off. I can just multiply this by n. So m times n is 2k times n, and k times n is an integer, so is even. Hence, m times n is even. And then case 2, n is even. Okay, in this case, then n equals 2k, okay, in the integers. So m times n equals m times 2k. So maybe I'll write this as 2mk, and m times n then is even. So I'll say hence m times n is even. And that concludes the proof. So I did it. We got the forward direction and backward direction. We had to do the forward direction by cases and contrapositive. And I didn't use this without loss of generality. So I wanted to show you the full proof first before I show you where you could have saved some time and work. Notice that case 1 and case 2, my argument would be exactly the same if I just switch m and n. Like if everywhere I just switch, instead of writing m, I write n, then case 1 is turned into case 2, almost exactly. That is, there's nothing new that's added in case 2. It's basically the same as case 1. So why even write it? Well, that's a good point. You don't have to write it. You can say, so let me redo this bit and show you how you could have rewritten this and saved some work. So we would say, okay, we're doing the forward direction by contrapositive. And we would say m is even or n is even. Our assumption is the same. But what I'll say now, upon realizing that these cases are going to be identical, I'll say without loss of generality, and usually abbreviated, another case of being lazy, without loss of generality, assume m is even. And then I just would have given case 1 where m is even. So yada, 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 then m equals 2k for some integer k, and finish off the proof. It'll be the same as case 1 above. So I could have actually gotten away with writing this proof with just doing one case. When the two cases are going to be identical, you can say without loss of generality and just do one case. Now, you have to be very careful about this. You have to make absolute sure that both of the cases are going to be identical. So how can you recognize when to use without loss of generality? And the idea here is that if there's some kind of symmetry in the statement, then you can use without loss of generality. So if I go back to the statement I'm trying to prove, m is even or n is even implies m times n is even. If I switch m and n here, so let me maybe rewrite this over here. N is even or m is even implies n times n is even. So if you just kind of mentally do this switch of your variables, and it doesn't change the statement at all, right? N is even or m is even, well, we have commutativity of disjunction, so that's the same thing. And n times n and m times n, those are the same thing because we have commutativity of multiplication. So this is exactly the same statement. Whenever you're in this situation and you have to break it down to cases, you can use without loss of generality. So that's one way to see it, is some kind of symmetry in the statement. By the way, we actually used without loss of generality on the first week with the friends and enemies. If you go back to that, if you care to do this, if you go back to that, you'll see we made some assumptions, and basically they boil down to this idea of a symmetry in the statement and not having to do every single last case. All right, that's it for this video. I'll see you next time.